Yes, well, I think I can clarify the last thing I said. A little too dramatic, I suspect. The twin prime problem plus Goldbach plus a general formula. When you put in a number, you get the numbers prime. P of 218 is 573. Golden fleece or something. I think it's still sort of right. It's going to be complicated to get there. Here's a couple of easy ones that I'll do first, just to show you I can connect with normal kind of things. The Chinese remainder theorem is involved with, we'll call it my prime base idea. Okay, the Chinese remainder theorem is pretty well established in most books on number theory or general mathematics. The one I'll use is from David Nelson's Dictionary of Mathematics. They're all the same, obviously. And it's, I don't know, it's not exactly crystalline, where it comes from or why, at least from reading these things. So it has to do with solving a system of modular equations. And here's how they express it here. If you have M1 through MR pairwise relatively prime, so I'll just say, so certainly the primes themselves fit that bill, are such, 2, 3, 5, 7, stuff like that, are certainly pairwise prime. So if you have those and you have set A1 through AR, and they say any integers, so I assume that means positive, negative, 0, then there exists an X, not quite unique. I don't know if it was just my teacher in set theory a while back, Cohen by name, who said it's unique if you put a explanation mark next to the existential, is that what they call that notation there? Any integer, then there exists an X. It's kind of unique. Okay, and then there exists an X such that X is equivalent to A1 mod M1. X is equivalent to A2 mod M2 dot dot dot. X is equivalent to AR mod MR. Now, why this connects with the prime base idea, I've often wondered this. This means I can, we can, or anybody can. So this means I can specify digits, in effect, digits in the prime base, and know there is a number associated with it. So in the prime base, let's try something like 5. That's going to be remainder of 1, base 2, the quotient of 2. 2 times 2 plus 1 is 5. That's the prime, first prime. And let's go to the second prime. It's 1 times 3 plus 2. Okay. And let me see if I'm notating this right. So let's do another one here. I think do I include 5? Yeah, you could do 5. Let me see here. So 5 has a remainder of 0 and a quotient of 1. 5 times 1 is 5 plus 0. Okay, so these are all modular ideas with the remainder. This says 5 is equivalent to 1 mod 2. 5 is equivalent to 2 mod 3. And 5 is equivalent to 0 mod 5. So these are the digits 1, 2, 0, and x in Chinese remainder theorem. So I can make up any 3 here and know that there will be a number associated with it. I didn't think that was true. I thought they would kind of all locked in. This is really 5, this is really 5, and this is really 5. They're all reflecting the same thing. So the fact that you can put in anything here and it'll crunch out an x for you, was that kind of interesting? I'd have to think about that for a long time. It doesn't quite help me. What would like is I'm given A1, let's make it A2, A3, A5, ... for some number, say P sub K, the kth prime, and this is mod 2, mod 3, mod 5, ... mod pk, and somehow I crank out of this, crank out x, let's say plus minus x, that takes us to Goldbach pair, Goldbach cell pair, 2 primes that sum to 2x, that sum, let's tighten this up here, that 2 primes crank out n plus or minus x such that 2n equals p1 plus p2, where n plus x is p1 and n minus x is p2. And it seems related, that you put in your n, you specify your n here, with the digits for n and these primes, and it cranks out, or it says there exists an x such that when you, take n plus or minus that x, you get these primes. It seems related, but I've twisted this around in my head, and I don't think the Chinese remainder theorem gets you there. It says that a number exists for this situation. Well, we know that number. That x is our n. So we come into it with what they go out of it with. So it doesn't quite do it. But that's, I didn't think that would work. I've read, as the various notations in this book will indicate, that this book pretty well. I don't find it a particularly attractive book. I don't find, as I said in a statement somewhere, that number theory books are particularly, up to the task somehow. I think this is much more interesting what I'm doing here, where you really get into a spreadsheets and you have a quest and a motivation for the Chinese remainder theorem and research. I think it tweaks or piques your natural curiosity. I'm obsessed with Goldbach, which, if you have genetically, some kind of predisposition and you are in the right environment, that obsession comes out and you become a number theorist. These books, relative to me, you have to strain to get that emotion, that obsession evoked. Whereas it counters what I have naturally, as do many teachers, and some teachers do not. Beatty, Lindsay, a few others got me, into it, and said, no, this kid's kind of into math, so I guess that's what they said. So, if we can cut him some slack, that's all right. Just let him do his thing. It's kind of unfortunate that you go to various math classes and you go in with a lot of enthusiasm, some articles, some results, and you go out, with your tail between your legs and defeated, kind of, I hate math. Does that work? And books can be like that too. Number theory books seem to be like that. Calculus books, they're probably old enough and applied enough that, and all those things imply you have, 1,500 editors, illustrators, checkers, stakeholders making, Larson's calculus book or Stewart's or, this guy and that guy's book, and it's, going to be good, and charming, maybe, even that. I'd say, they try to do things. Blitzer, in particular, I'm finding, is thinking mathematics. Does it really get you to think mathematically? It has these pictures and illustrations, but it's not really doing it. Okay, my next thing after that is to try to show what I was saying before, that you can get a complicated induction. When I say complicated induction, I'm not kidding around. Where instead of, k implies k plus 1, you have, 1 through 24 with a pattern implies 25 through 48 with the same pattern, and so forth and so on. The base case is, checked manually. You develop a complicated procedure, the theorem up here, I'll just read it. Primes 2 and 3 are such that they can find, using plus or minus x, other primes, n plus x minus x, such that n plus n minus x, or p1 plus p2 equals 2n, for all n between 3 and 21 inclusive. And you develop a rule for your n, that you go up by x and down by x symmetrically with your n, and you'll find the two primes. So down here, see if we can do this. You have a kind of symbolization here. If they both have remainders of 0, it has this x in the middle. If one has a remainder of 0, that's the composite. You could call this a 3 prime. The remainder upon division by 3 is 1 for this 4, and 0 for this 4, given your prime is 2. So the 0 makes this composite. You can call it a 3 prime, that its division when divided by 3, you do not get a 0. Now, if they're both 0, that's one case, as in here. If one is 0 and that's the other, then you get these cases. If they're both non-zero, that's a new prime. Up until 25. At 25, you do get 1 and 1 indicating a prime, but 25, and you can start tabulating these, in mod 5 is 0. That's not a prime. It's after the first 5. It's not a prime. But this pattern is symmetric. You can, I think, see it, or I can tell it to you. X, nothing, forward slash, backslash, forward slash, nothing, X, nothing, forward, back, forward, nothing, double, nothing, forward, back, forward, nothing, double. It repeats. It's symmetric. And you can have a rule that if you're here, then you're done. That is a prime, and you use it for the sum of two primes, gives you twice this, twice 11. If you're not there, you need a rule for the 4 other cases, and x, forward, and backward, 3 other cases. And that is given by use 3, x is 3, for a forward slash, backslash is +2, and if it's a double, use 1. That will always get you to a 2, 3 prime. For these numbers, and given that 24, or let's see here, 24 starts there, these are symmetric, starts with an x, ends with an x, I can just repeat that, and I'll have the same block of symbols for 24 through 48. And I can, on occasion at least, predict 39 and 41 are twin primes, because back over here across the page, let's see if I got this right, 41 and 43 correspond to 17 and 19 back here in the previous block. Now, occasionally you get, for example, 29 and 31 do go back to 5 and 7, another one, a success story. I can, I have to think about it some more, predict a twin prime from a twin prime here. In the earlier twin prime, I go to a perfect square and I tack on this structure, and they'll be offset but reoccurring in a predictable fashion. It's not easy to get this function to be concrete, but it is, I think, my whole program here is to see if I can specify rules. You duplicate this, you can keep on duplicating it, right? You're not going to break anything. You start with another square minus 1 I think is what I'm doing here, And at some point, you add, when you no longer are getting primes correctly, as in 49 needs a 7 to block that from being considered a prime. You get 1, 1, 1 and 2, 3, 5 indicate a prime. But the 7, when that's added, which you can do way back when you get the first 7 back there, indicated it's not a prime. So you need to refine these, adding, in effect, a sieve as you go. Does that addition of a sieve, is it amenable to new rules that you can algorithmically specify? That's the question. I think it does. Once you have the rules specified for this block, which I just gave, then when you add a 5, you tune it per the cases. Like here, I have 1, 2 indicating prime, but I have a 0, a slash there indicating the 5 is the problem. But then I have a rule to add 6. If it lands on a 5 with my previous rules, I add 6. And that always works. And you can also see why it works. You're getting the 6 will keep the modularity of mod 2, mod 3. And the 6 will change the mod 0 for 5 to a non-zero. So because they're symmetric, that rule works. So for 35, I think I go to 31 and 39, or 29 and 41. 29 and 41, 6 away from that center in a symmetric way. This repeated, it's a complicated induction. I've never seen something like this, where you assume you have it for a bunch of blocks, then you construct another block. You assume you have it for your blocks, and then you copy and paste, make your rules, your notation, and a theorem says you'll have it for the next block. K implies K plus 1. And the total picture is all natural numbers have a x such that when you add and subtract that x, you hit a prime. You hit 2 primes, and that it's immediate that the sum of those 2 primes is 2 times your number. And that's Goldbach. And maybe in there at some point you could say you can predict, or just go to, there's an infinite number of twin primes, and maybe you can get a prime function, put in P of n, get the nth prime out. You could see how the previous is to a block predicting the future. It's offset, it's modified for new 0 modularities, but it's probably not in my lifetime that I would be able to do that. I might be able to get Goldbach to fall out of this, maybe the twin primes. One last thing. I mentioned that you can teach number theory one way or another way. For me, this is a nice way. Of course, I'm a student of one student, and he's also the teacher in the class. But I just mentioned that the benefit of this, you could say number theory does nothing, but I'm finding I'm getting mentally more and more organized, more and more obsessive, compulsive. Another way to look at it, I have Costco lists that I sort by sort of location and theme, canned versus fresh, aisle 22 versus 17, things like that. And I've added to that maintenance of our condo here, a block for that, a to-do list, and an appointment list on the same sheet. Here's a wild one. When I change my sheets, I remove the bedspread. The bedspread has a little tag on it indicating where the bottom is to go. It's that's the base of the bed, the little red ribbon there, so I know it doesn't go this way, it doesn't go that way. I can orient the bedspread. Well, before I would just take the bedspread off and throw it on a chair. Now, a la my induction idea, I carefully fold it, place it in a certain position so that the red tag remains prominent, and I can unfold it and perfectly reconstitute my bedspread after the sheets are washed. I'm thinking of getting some kind of markers on the sheet so it's not sliding too far to the right, too far to the left. You get one established and the other one will also be established. All this kind of logistics that's going on mentally seems to be falling out from this obsession with the number theory problem. A benefit, I think, or interesting at any rate, that it gets you organized. It gets you to think, out of the box. Probably all of these numbers, their cyclicity is somehow deep in the structure of our mental works, and it kind of, that's feeds into the obsession. You're figuring out, you're resonating with your internal mental works, and that's why you're interested in this stuff and pursuing it. All right. I think maybe I did both things here. I guess that's it.